About the first part of the course, which is Introduction to Quantum Computing. And again, just as a reminder, this is a playlist in preparation for my course with Pearson and O'Reilly on the topic of quantum AI and cybersecurity, which is happening on the 2nd of September. I do have other courses with Pearson and O'Reilly, which are coming a little bit later, and you can subscribe to those. So this one is on the 15th of September. AI attack surface. I have another one which is on agentic AI risk. That's on the 10th of October. But if you don't have Pearson and O'Reilly subscription, you can subscribe to the YouTube channel here, and you're gonna get my preparation for the course material. Obviously, these courses are delivered to professional people that they want everything to be planned, structured, and time managed. And on these videos, it's a little bit more relaxed way. This is my preparation for the course, basically. So we're going to be talking about basics of quantum mechanics and quantum computing, and this playlist will expand into all of those other topics. So if you subscribe, you're going to be getting like one video every day on different topic, and then you would be able to watch them all as a one course of 4 or 5 hours in total, if that is what you desire to do. The idea is to explain what is the quantum AI, what is the risks and the benefits of quantum AI for cybersecurity, because quantum AI poses different threats, but also quantum AI can be used for cybersecurity. So we are looking at the two sides of the flipping coin. Just a little bit background about myself. You can click here in that link and you would find my profile. I work mostly in attack and penetration. I don't work in defense that much, so there's a whole list of Pearson and O'Reilly courses that I'm teaching on my profile. You can just type my name, so that's my name. You can just type my name in Google and you can get loads of information about me. Moving on to the actual introduction to quantum computing. So you see how I have prepared this course material. So if I go to introduction of quantum computing, if you do this, boom, magic opens all the windows. This is a trick with Google Chrome. Starting from the first one, so instead of me telling you what is quantum computing, I'm going to use existing literature. So I'm going to be showing you diagrams that other authors have written, and then I'm going to explain it with my own words. Quantum computing for norm physicists, this is one of the most cited papers on the topic. It's from famous authors that they have published, and actually it's considered as, well, not this one, but the second one. This one is considered the Bible of quantum computation and informations. So we're going to have that book over here. But starting from the first one, if you're not familiar with Archive is a preprint repository, which means that everything is open source. You can click on the link here, and then you're going to be able to read the actual paper. So let's click and see what's the difference. If we click over there, maybe it's going to ask for subscription. Depends if the authors had open access. So if you go to Google Scholar and if you look at my papers, for example, they're all published in open source because University of Oxford pays for. So let me show you. So Google Scholar. So that's my profile, and if you open my Google Scholar, all of those articles here, if you click on it, it will give you the PDF file. It's not going to be asking you for any money or any subscription. So I'll just demonstrate that. So if you click all those clicks and download the PDF, and now it's going to be downloading the PDF for you in I don't want to download my own paper. So hold on, how do I close this? New folder, maybe. Okay, so now I need to shift this. Okay, so now that is saved into my desktop, and if I wanted to go and find that, I can open it. So that's it, that's the paper. There's no subscription, there's nothing. And that is the case with all of those articles that you can find on my Google Scholar profile. If you click here, that's all open access, but it's not always the case. So let's see this one. I'm just clicked and it's not opening. DOY, since it has a DOY and an archive, that actually means that this paper might have never been published, or maybe it's published, but let's see. Let's try this differently. So if you Google that, okay, there it is. So that's the actual paper. It's in ACM.org. This is getting boring, so I'm not going to do this again. Just for the first paper. I'm not going to do for the rest of them because just time passes by and we're looking at. So if you click here, if it's open access, you would be able to download it, and there you are. So you can download this, but if for some reason, when you click, if it's asking you for subscription, then you can go back to archive, and you would be able to download the paper as a preprint from the archive. I'll show you how to do that with a different paper. But this is a very long and very technical explanation of quantum computing for non-physicists. Well, quantum computing is predominantly physics. So this is, let's stop at some point. So here maybe, that seems relatively simple. Let's use this part. Quantum computing can run simulations. If you're familiar with probabilities you have like, this is based on probabilities. That is also based on machine code. So in this context of quantum computing, machine code, it's based on zeros and ones. We have programming languages like Python, C++, JavaScript. That's not machine code. That's just the interface for humans to interact with the machine. The machine code is zeros and ones. That's it. And with the current mathematical computers, you can run simulations, but they're very slow, because if you want to run all of those, it would do them one by one. Quantum computer can run those states in the same time. So that's why it's much faster. But it's based on physics, it's not based on mathematics. So this is a fundamental difference why quantum computer is faster than normal computer. Normal computer would run this one, then that simulation, then that, and then it will give you the results. And a quantum computer will just run them all in the same time. So that is a non-technical explanation of this very, very technical paper. If you want to read it, as you can see, it's open access. This is one of the most read papers on quantum computing. So there you are. You have lots of sigmas, lots of gammas. I'm not going to do that to you. I'm not going to read all that. But here, just to demonstrate, so this is the actual paper. But if you want to, if for some reason, when you click, like on my papers are all free, let me close that. This paper is also free in open access. But if for some reason, when you click, it's asking you for a subscription, then you can do this. You can just view as a PDF on the archive. So you're going to see the preprint version. And what the preprint version is basically the same paper, just without the minor editing. This is the accepted paper, basically. So, but just the formatting of the journal is not here. There might be one spelling mistake, two spelling mistakes. There's not going to be much difference. So if you don't have resources and if you don't want to pay the journal subscription, this is one way how you can read exactly the same paper without paying for the subscription. It's a good trick to know. And I'm surprised that many people don't know this. That we are encouraged to publish in open source. That's why my university, University of Oxford, pays for my papers to be published in open source. We are encouraged to do that. But journals have to make money. So if you want that niche and polished formatting, you have to get the subscription. But if you want to know the technical details of the paper, just open this and read it. I'm not going to say any more about this because, as I said, it's just how it works with every single paper. It's a good information to know, but we need to move on to the next one. So here we have the Bible on quantum computation and quantum information. This is considered as the the main book. Hold on, let's see, maybe it's written. So it's formerly known as Mike and Ike. Book assumes yada yada yada. The book is elementary, starts with the assumption that the reader does not even know quantum mechanics. So this is a good starting point. I'm surprised that they say the book is too elementary. Nobody understands quantum mechanics. There's just lots of smart people pretending to be very smart. Quantum computing, it's a very, very difficult thing. There could be like 3 or 4 or 5 people in the world that actually can contribute technically to the quantum computing, and they say that they don't understand it completely. That comes from them. So if some academic with who just has a big ego tells you that they understand quantum computing, just take it with a pinch of salt, because they don't. Simply they don't. How do you know that if they do or they don't? Go to this Google Scholar profile and see what they have published in quantum computing, and that will give you a profile if they actually know. But as I said, there's like very few people that they understand this topic, and this is the Bible on quantum computing. This is just a table of content, the one you can expect to read. It's it's not a fun read, you know. So let's see what's in the book. This is the actual book. It's from Cambridge University Press. Let's try and find some image. So we are looking for for an image here. Download flyer. Nah, that may be too. It's interesting that they don't give you a graphical abstract, which is a shame. So we know the content, okay, authors, we know the authors. Are they still alive? Let's see if they're still alive. Is this person still alive? He's born, that's age 51. He's not even that old. He's Austrian American, okay? So the first author is still alive. Let's see if the second author is still alive. Awards, doesn't say. It doesn't say what year he's born, but he undergraduate degrees in physics in 1990, so he graduated in 1997. He received his PhD from Stanford, so he's not that old. Hopefully, he's alive. I honestly don't know. You know, I don't know if Isaac Chuang is still with us, but some of the leading authors of, for example, Peter Shor, who is also at MIT, he is still alive. And Peter Shor wrote the Shor algorithm that breaks all the RSA encryption and confirms that quantum computing is an extremely risky thing. So we're going to be talking more about that. I cannot find any good images on this book to show you. Let's see if we can download the flyer just to see if the flyer is going to give us something that we can explain. But obviously, we're not going to be going through the entire book. They say that they are easy to read, and they say that it's for anybody to understand. It's quantum computing is very technical subject. So there's nothing here. Okay, so we're going to look for something better. We're going to close those. If you want to buy a book, this is probably the book on quantum computing. It's considered the Bible, but it's not going to be easy read. It's going to be full of formulas, numbers. So we're going to be looking at different alternatives. So here we have a brief introduction to quantum computing. It's another interesting read. And for this one, you will be able to download it. So you just click here, download, and you can download it. And by the way, if you attend the course that I'm going to be teaching tomorrow, those links would be included like this. And also, I'm going to include them as references in a bibliographic format. So this is the more formal and official references where you can go and search them on the internet. I'm going to provide them in the link that you can just click on those. So if you click on any of those links, it would lead you to, so for example, this one is the one, I think this one is the one that we're currently looking, brief introduction to quantum. And here, there we are, brief introduction to quantum computing. It looks better because it has Figshare. When I publish anything, I always include Figshare because here you can, download some figures, and I don't want to cite it. Okay, explore more content. But it has some interesting figures. How do I reduce this? Can I even reduce that? No, this cannot be reduced. So you might be better off to download, to use that other button that we had here that you downloaded. Let's see if I download it, what's gonna happen. Okay, so appendixes is just downloading the appendixes. Let's look at this. Appendixes. No, I deleted it. Why did I delete that? Okay, so it's gone. It's deleted. I'm not gonna recover that. Let's see if I can do this. Aha. Okay, there we are. That's better. That's much better. Now we have an explanation of quantum computing here. This is just a sphere, Q-sphere, that is frequently used to explain how quantum computing works and why that zeros and ones they are performed in the same time. But let's try to explain it differently. Why are zeros and ones always happening in the same time? With a quantum entanglement, once you impose a certain state to one particle, the second particle changes the state instantaneously, faster than the speed of light, or at the speed of light. I'm not in physics, but it's very fast. So when they've done the experiment, they've taken one particle in Europe, a second particle in South Africa, and they've put a very smart watch that was measuring the milliseconds, and they manipulated one particle, and they waited to see how long it's going to take for the second particle to change and to reflect on that. And it was changing. Einstein called this the spooky action in the distance, that you once two particles are entangled, if you would separate them and you put one, theoretically you can keep one particle on planet Earth and a different particle on other side of the universe, and they should uh, share information. So as soon as you influence one, the second one should change. But how does it work with the faster than speed of light? That I don't know, because I'm not into physics. I work in cybersecurity. So if one particle is in Europe and the second one is South Africa, which for us in cybersecurity is enough to know because we're not planning to go to the other side of the universe. But if those two particles are, if the communication is happening at the speed of light, we cannot reach speed of light. So that for us is almost instant. You can have multiple states happening in the same time. But you know, if that particle was at the other side of the observable universe, which is like 13 trillion light years traveling, I don't know how long it's going to take for that particle to change. You need to ask physicists for that. I work with practical and applied things. I work with Python code that you can actually develop an app, press the button and get the job done. I don't work with what could happen. I have never been to the other side of the universe. I don't know what's on the other side of the universe. I have no intentions of going to the other side of the universe, even if I could. So the discussion on what would happen there, I'll tell you once I get there. Since I cannot get there, for me that is a pointless discussion. There we are. This is the second book that you can read. Again, I didn't see any good images here. And you know, when they say this is the most read books, not many people actually read this book. So you can see here 156 views. One of those is mine that I just hear, 88 downloads in total. So, yeah, not very good. Let's see Google Scholar. If we can find this one on Google Scholar. How many citations does it have? Let's see. It's only cited by one person. I could be wrong, but that one, I've showed you a second book, and I still cannot find a good image to demonstrate how it works. Now we have the third. This is quantum computing, a taxonomy, systemic review, and future directions. Future directions from year 2020, so that's 5 years ago. And here, as you can see, this link, it's still an archive link. You might find it the same way that I did with the other one, but I'm gonna open the preprint here just because it's easier and it's gonna be the same paper. That's the only reason. But I'm sure that you can find this paper published in an actual journal. And if it has restrictions on viewing, you do what I did now. So here we are, and this journal paper has loads of interesting diagrams, and this is one of the reasons why I prefer journal papers. First, they're free. You don't have to pay for them. Even if I didn't have subscription, which I do to most of the large journals, universities, if you're a university employee, the university pays for your subscription. Actually, everybody that I know has subscription to Pearson and O'Reilly. So if you work for Cisco's, Google, Amazon Web Services, if you work for a university, you don't know, but probably your university would provide you with a subscription. Also, in the same time, you would have subscription to Elsevier, Springer, and those journals. So I use Archive just because it's faster, but I do have a subscription if I wanted to read this, and I still don't use it. So here we have nice image that is explaining not very much. Okay, bit, qubit, qubit. So here we have superposition and entanglement. So those are the two things that I explained to you with the example of taking one particle in Europe, a second one in South Africa. This is just an explanation of how once you manipulate one, once they're entangled, at the distance they would be able to communicate. You can explain this in very technical terms with formulas, but that's all it does. That's all it is. So Einstein also had a different saying. He said, if you cannot explain something in a one sentence, it's not very clear to you. So if somebody comes to you with loads of formulas and mathematical things that you don't understand, just keep that in mind. According to Einstein, if somebody cannot explain it to you clearly with a single sentence, it's not clear to him. So I explained to you this with the example from other side of the universe, with South Africa, and hopefully this makes sense. It's just, this is the first particle, that's the second particle. You take the first particle in Europe, first you entangle them, so you make this entanglement, and then you separate them, and they can communicate at a very fast speed. So that's quantum entanglement. So here we have nice, interesting diagrams, quantum computing taxonomy, so you can look at all those building blocks. By the way, in some of the other courses, if you subscribe to this, in some of the other videos that I'm going to record, I'm going to be talking about blockchain. So blockchain and quantum resistant frameworks, future proofing identity systems. So most of the digital identity systems, not only Facebook and social media, but also some of the decentralized identity systems when you manage your own money, like with MetaMask and different blockchain wallets, when you have no banks controlling you. That was the invention of Satoshi Nakamoto in 2009, that he got upset with all the banks collapsing in 2008. And now in the UK, they imposed a levy. This is in the, hold on, many people don't really know why Satoshi Nakamoto created Bitcoin. UK bank levy. So let's look at the news. We're going to the news. Bank share price tumble after global price. Why is the United Kingdom imposing a bank? I don't want to sign. I don't want to. Maybe later. Okay. Accept. Why is the UK imposing this bank levy on most of the UK banks on profits? Because UK still hasn't recovered all the money that they spent in 2008 rescuing banks. So is it fair to impose this 8 billion a year tax levy? Definitely. Is it going to help the banking sector? Probably not. Is it going to help the UK keep them, dominant place in the world as the banking services? Probably not. Definitely not. Because banks, they want money. So if you impose these levies on them, they're gonna go somewhere else and conduct their business in Frankfurt or Berlin or New York or Tokyo. But UK has to recover the money that they have spent bailing these banks. And this is the reason why Satoshi Nakamoto in 2008 created Bitcoin, because he was upset with these banking giants just pumping up money and unsustainably spending your money, and then asking for money from the government and deflating your currency with various different methods like inflation, that money loses value. So we're going to be talking about blockchain and digital identity systems and how those would be hacked by quantum computer. But here you have a taxonomy of building blocks, future directions. Let's see if decentralization is anywhere in this energy management. Okay, so energy management, quantum assisted machine learning, we're going to be talking about that. Robotics. Robotics does not require quantum computing. Let's just, based on this diagram that comes from an academic literature from very established journal, let's be a little bit critical. Where would you use quantum computer? Not for your everyday use. If you think that one day you're going to have a quantum computer that you're going to play and you watch YouTube on it, that's not going to happen. That's just not what quantum computers would be built to design. There would be quantum computers would be built to analyze databases, large databases, and break databases, like do things like that. But it's not going to be practical to use it for your everyday uses. So, simple things like robotics. How would you fit a quantum device into a robot? It's a robot has to move around, and your Hoover or your car. Quantum computer requires a big cooling mechanism. It has to be maintained at a sub-zero temperature constantly, otherwise it loses all the properties. So it's very difficult to see how would you fit that into a very tiny little robot that can fly around like a drone. That's not, in my opinion, I don't think that's ever going to be a case. But things like quantum internet, yes, because internet is maintained with databases and yada yada yada. Quantum assisted machine learning, yeah, definitely, because that's going to be centralized in a specific place where you feed data, analyzes the data. So I hope this makes it clear what would quantum computing be used for and what would be not used for. It would never be used for laptop devices to empower you to, I don't know, stream really fast. It's never going to be used on IoT devices. It's never going to be used on small, tiny. It's going to be based on databases. So mostly I would imagine in cloud environments. So you have Amazon Web Services that many different IoT devices and very small cameras are feeding data, and then that cloud is analyzing the data with a quantum computer. That's where the power of quantum is. You won't really need a quantum computer if you can stream YouTube and do all the things that you need with a normal computer. Now, this is enough on this paper. Let's see if there's something else. No, it's just interesting diagrams. I assume this is designed with a app like Miro. This analysis of literature. Okay, there's lots of confusing diagrams. It's very difficult to fit everything into a diagram. That's why usually journals are very case specific. But those are interesting diagrams. If you want to read this paper completely free, you can open source on Archive. What I'm showing you now is I have no subscription to open this paper. Moving on to a different paper. Let's see, why do we have that? Reject non-essential. Okay. Now we have artificial intelligence and machine learning. This is from a different journal paper published on 3rd of January. Is it open source? Let's see. It has lots of images, so that's why I have selected it. When I was looking at how I can explain this part of the course, which is Introduction to the Quantum Computing, the basics of quantum mechanics and the quantum principle, this is just like all of those sections here would be just 15 minutes in my course. Although, why am I using that? This. Okay, so that is all going to be 15 minutes in my course. And as you can see here, it's very difficult to fit everything into 15 minutes, especially when you have to teach something like quantum mechanics and quantum computing principle, which is one of the most complicated things. And that should be done in like a couple of minutes. So for that, you need to have images like this. So this is an image that is explaining how neural networks and machine learning techniques would be applied in neural networks with the dense classification. So this is one figure that I don't have to create. So then it expands into estimations of the neural networks, copies of a quantum state that can be processed to produce an estimate and the quantum state. So this is state estimate from many copies, then state update, then learning many particle statistics, and restricted Boltzmann machine. If you're not familiar with this Boltzmann machine, that's one of the very early stages of artificial intelligence. Boltzmann machine. Hold on, let's find Boltzmann machine. Boltzmann machine. Probably I misspelled it. Yes, there it is. So this is how a graphical representation of a Boltzmann machine. When communication, this is not how neural nets are operating today, but this is one of the original concepts of AI. So that's all that we have. And now neural nets are mostly this restricted Boltzmann machine. You see neural nets are building like this, and then they expand into more layers. And the way that I explain it usually is that they would have a different section here, different, and those are like tables. So when machine is trying to learn, is basically like you're sending a prompt, and it's like a ping pong ball, and it has to reach this end. And you send it from here, hits one table, hits another table, and then strays off. Okay, it tries again. That's the wrong thing, the wrong answer. So it tries again, hits the third table, then strays off. Okay, then the machine tries again. This is how machine learning works. And eventually it will hit all those ping pong tables, and it will reach the correct answer. So this is the correct answer. Yay! That means that machine knows that this is okay. So then it can verify the answer if it needs to. But Boltzmann machine, to have these simple two layers, it's the basics of machine learning. So here we have restricted Boltzmann machine as a sample. Let's see what other diagrams do we have. We have model-free reinforcement learning. Reinforcement learning, on the other hand, is a very complicated format that is really scary if you can combine reinforcement learning with quantum computing, because of the three categories of artificial intelligence that we have, of machine learning, let's say. So today, if we separate machine learning into three categories, so first one is supervised, second one is unsupervised, third one is reinforcement learning. So here we're talking about the third category. The first one is when you put labels to all the data. So you have various different bananas, and you say, okay, this is bananas, and the machine learns what is a banana. Second one is you have loads of bananas, and then you feed that to the machine, and the machine learns, okay, those are bananas without label. So first one is you label and you tell it what it is. Second one is just feed loads of information. Machine learns on its own. Reinforcement learning is a combination of both, but then it has this action. The action is when it learns from the environment. So this is the environment, and then it gets like a reward if it wins instead of the ping pong tables. Then it goes back in circle and feeds that to the robot, to the machine, and repeats this process all the time, learning from the environment. So if you have a quantum computer and reinforcement learning, imagine how much machine can learn from everything that is happening without human intervention, without labeling, without anything. So you just release it out in the world, and it would use the computational power of the quantum computer to learn everything that there is to learn. Quite soon it will get very, very smart, much smarter than us, although it's not going to have as many neural connections as we do. So it's going to do that. It's not only that it's going to be smarter than humans, but it's going to do it more efficiently. So human brain requires lots of energy to replicate the human brain. As in a computer, you would need to use all the current computational power on the planet world, on the entire planet, all the computers, everything, all the data sets, just to build one human brain as a computer, just because we have too many connections. So the human brain, to replicate the human brain without putting it into a human system, it's quite challenging. You need loads of computational power. We don't have that. So the neural nets would do the same kind of job in a narrow field, but without so many connections. So it's gonna be faster. So that is what we have here, extracting concepts of discovery from quantum entanglement, and this is an explanation of discrete control gates and syndrome interpretation. So zeros and ones. So we spoke about zeros and ones. So let's say this is in Europe, that's in South Africa. And all those zeros and ones would, as you change them in Europe, they would instantly change in Africa. So that is a very fast connection that you're gonna have over there. Okay, this is probably enough about this paper. You can download it as a PDF over there and read it. I guess open source. This is from the Cloud Security Alliance, and here we have, what do we have here? We have interview of two sisters. So I have seen this interview on Quantum Computing 101, when two sisters would be probing questions and answers in order to answer what a classical computer is and how is it different than a quantum computer. I did find this quite an informative, and there's a video at the very end that you can watch somewhere on this link. Oh, there's no video, okay. So the video is in a different place, but this interview is recorded. You would find a link somewhere in this. This is from the Cloud Security Alliance again. Quantum artificial intelligence, relationship between AI and quantum computing. This is very recent, actually, from this year. There's not much work done on the combination of those two, the AI and quantum computing. Actually, if you Google quantum and AI cybersecurity, this course is going to be one of the only results. I demonstrated that in the first video yesterday, and that's the reason why I wanted to record this, so we have more information. So, and this is going to be a playlist again, that you're going to be getting different videos coming up every day, otherwise it gets really long. And why am I recording this? I'm practicing. So if I'm still on the first one and I have to compress all those topics into 15 minutes on the course, so I'm gonna have to speed it up for the actual presentation. But this is a video between two sisters, and you can Mehak and Megna, those are the two sisters, and they would give you explanations of first of quantum computing. First, this is the first part, quantum computing. Then is the second part, which is the artificial intelligence, and then how can AI help with quantum, and how can quantum help with AI? Why is this circle floating? Why is there's nothing opening? So anyways, so here it's just a discussion between the noises, for example, decoherence, noise reduction, quantum advantage, and cleansing data. There's a lot of data that we never store, we never use, we don't do anything out of it. So imagine the oil rigs, they have all those various different IoT devices sending data via the internet. There's no way for us to store all that data about the waves, about this and about that and about the environment. Well, quantum computing can cleanse that data and store only the data that is required. So I'm going to close this. If you want to read the whole interview between the two sisters, you can go to Cloud Security Allowance, type this, and that's it. Okay, so this circle that was going around, it disappeared. I think it was related to that specific web page. Okay, so here we are, review of quantum cybersecurity, threats, risks, and opportunities. As you can see from the title, quantum cybersecurity. There is no AI quantum cybersecurity. This, as I said, there is not much work done in the combination of the two fields together. They're always looked in isolation. Why? Because they're so difficult to understand, even when you look at them in isolation. When you put them together, it's extremely difficult to know what the risks are. But we're going to cover all of that in the course that we're going to be uh, teaching. And if you want to know more about it, subscribe to the playlist. Here, this is again open source document, and there's loads of. This is just an explanation of the systemic literature review. This is another literature review paper. Let's see, publication source by type. So here you can find the yellow is conference, as you can see here. Blue is journal. So as you can see, that number is increasing in 2020. This is from 2021, and that's from 2017. So the types of publications on the topics of quantum computing and cybersecurity is increasing, and it's predominantly in journals and conferences. The gray here is article, so it says that here that's a news article. This means non-peer reviewed. But in 2022, there is a shift here. There is a lot more of those news articles. So something happened. Something happened in 2021 that triggered this shift. That you have more. There's less conference papers. There's more journal papers and more news articles on this specific topic. Here is some explanation of the post-quantum public key crypt systems taxonomy of the main practical implementations. So here I imagine that if you look at those, you would find specific implementations. The lithium, also, hold on, the lithium Falcon, those are the post-quantum cryptography algorithms selected by NIST. Kyber, that's over here as well. Encrypt, so that's again on the NIST post-quantum cryptography, so I can see what he's reviewing. So here we have an illustration of the model of key shield, how key shield is protected. Let's see if we get another. No, that's it. That's the end of the paper. I'm going to close this one. Let's see, accept all. Quantum computing and cybersecurity. This is from the Belfer Center for Science and International Affairs from Harvard Kennedy Center. Now here we're looking more at the policy aspect of quantum cybersecurity. So again, you're going to get an explanation of what is quantum computing, loads of text, quantum architecture, impact of quantum computing on cybersecurity. So here it's saying that the different types of encryptions that we have, those symmetric and asymmetric, that's based on RSA, which quantum computer can break really easy. And he's explaining that the Shor algorithm is thanks to the Shor algorithm that we know that that's going to break. So it's a very long paper, a roadmap, okay? So here we have a roadmap of action agenda to advance cybersecurity. So from 2018, National Quantum Initiative Act authorized 1.27 billion funding for significant funding for private and private sector, public and private sector. Okay, let's look at this. Moving on, we need to find 2025 to see if this NIST post-quantum cryptography. Yeah, that's completed. Europe is now adopting that. UK is also adopting the NIST post-quantum cryptography project. It's just not enough time to repeat the same thing, and even if you repeat it, you're going to reinvent the wheel. So here we have quantum. I'm trying to find anything that would make this article worthy of discussion. But what I can see here is that this paper is again from 2021, so clearly we're not going to find anything from 2025 because this is published in 2021. But there's been a lot of work in the US on standardizing post-quantum cryptography. Europe and the UK has been, and the rest of the world has been slightly neglecting that part of the cybersecurity world, and now they're catching up by simply adopting the post-quantum cryptography algorithms from the US. I would have been surprised if they didn't do it. There has been lots of political debates that UK should have its own selection mechanism, Europe should have its own selection mechanism, especially from the European Union. There has been lots of voices, but eventually inevitable happens, NIST has done the work, and there's no point repeating that work. Actually, most of the algorithms came from collaborative work between Europe and US. Anyways, now moving on to the quantum computing explained. This is more recent from 20. Hold on, this is from 2025. What it means for cybersecurity and why is it coming faster than you think. Um, so the UK government 500 million investment in quantum innovation confirms that global leaders are no longer treating this as speculative but a strategic priority. By the way, those are the two main leaders, Google Willow and Microsoft Majorana, if that is how it's pronounced. Those are the two leading chips. So UK government is spending 500 million, but other countries are spending money as well. So what else do we have in this paper? It's not about adopting new form of computing, it's about protecting the system. So that's exactly post-quantum cryptography. It's not developing a quantum computer. Post-quantum cryptography is basically using mathematical algorithms to ensure that we are protected once we have a fully operational quantum computer. And by the way, Google Willow and Microsoft Majorana, they're making chips already. There's lots of other chips. So it's not like it's not gonna happen like ever. It's just that we haven't figured it out yet. But once we figure it out, it's gonna happen very fast. So here we have 67% of cybersecurity professionals believe that quantum computing will increase or shift cyber risk from the next decade. And I wanted to highlight that because if you have somebody from the background in physics, they're very skeptical that we're going to build a quantum computer. They're very skeptical that we're going to do anything. The truth is that 67% of all the cybersecurity professionals, they believe that quantum computing will happen in the next 5, 10, 15 years, next decade, it says here. And then it's going to cause significant problems for us in terms of breaking current cryptographic systems. Why do people in physics believe that quantum computing can never be achieved? Because it's very difficult to maintain the state of the qubits. So, who is right? Only time will tell. But I think there's quite a significant chance that we're going to build, even if it's a purpose-built quantum computer, just to break encryptions, because there's a significant interest in that specific area. And actually, even today, quantum cryptography is based on physics, post-quantum is based on mathematics. Even today, we can apply some parts of quantum cryptography, for sharing the public key. It's not operational. It's not going to work on large systems. It's not functional. It's not. I understand everything, but we have applied it in principle. So it's not like it's not going to happen. It's just that we're limited in terms of not many people know how to build this. If you look at the NIST post, and I will show you in some of the future videos, if you subscribe to the channel, or if you join the course here, you would see it all in 4 hours. But you would see that these algorithms are developed constantly by the same people, the same institutions. So that knowledge about this post-quantum cryptography and how quantum computers is very limited. Everybody else is just talking about it, but they don't really have the knowledge to build this kind of... imagine going to DEF CON, 30,000 participants, 50,000 participants, they're all working in cybersecurity. How many good hackers do you think there are in DEF CON? Not more than 30. Those are the good hackers, the people who can hack satellites and do things. Everybody else is just mediocre. And this is the same in any technical field. How many surgeons do you think that the world has that they can perform brain surgery? You can count them on your hand. It's the same with quantum. So, like if somebody tells you that if somebody out of those 5 or 10 people that actually understands it tells you that quantum computing is never going to happen, then you should start thinking about it. But so far, they're saying it is going to happen. That's why we're building these algorithms to protect. So here we are, post-quantum cryptography. This is Wikipedia page, and we're going to look at the actual NIST. Why am I using Wikipedia here? I just wanted to demonstrate that not all sources are equal. For some reason, we don't consider Wikipedia as a valid source, although it has really upped its act. Most of the information on Wikipedia now, it's quite reliable, but because everybody can edit, so I can go and change something on Wikipedia today, and give you misinformation. By the time it's actually spotted and changed, which will happen quite fast, but there's still that period, there's a gap in between where it could be misinformation. That's how Wikipedia is built. It's built on open source. People volunteer and contribute to the whole peer review process, so to speak. But you don't know who the editors are or the reviewers are. In a formal peer review process with the journals and papers, that happens, and then once it's published, you cannot change it. You cannot go to the journal paper and change things. So if you go to the Shor's algorithm here and look at the paper, you cannot edit that. You can only retract the whole paper and start writing a new paper, but you cannot change it. Wikipedia can be changed. So if you can create your username profile and go and change something here. And somebody else reads it in a different part of the world, in Indonesia, China, Asia, wherever, in US, and they might get misinformed. So that's why we don't trust Wikipedia. But if you know this, so I know that the Shor algorithm is one of the most credible sources, I can use it. Just that it's not the preferred choice for getting your information. So that's a long discussion, and then at the end I'm still going to use it because I know these things. So I know what the NIST has done. I'm using it here as my notes. I'm not using it to learn about it. I'm using it just to show you. So we have lattice-based cryptography adopted by NIST, hash-based cryptography, code-based cryptography. We have various different types of cryptographies, but NIST has selected the most effective ones, the fastest ones, the ones that you can implement without causing significant disturbance to businesses. So Makelis, this one is probably going to be approved this year. It's still currently under some form of testing. So here you have details about the signature basis and yada yada yada. Closing that one. How is that different? Hold on, let me reopen that. If I can reopen, why am I not? No, why? How did I go here? What is this? Anyways, that was post-quantum cryptography. That's based on mathematics, and this is quantum cryptography. So here we are looking at the quantum mechanics, and here we have an algorithm called BB84. It's going to be here somewhere. Let's find BB, or we can just search Command F, BB84. There we are. So this is one of the quantum, it's developed by Charles Bennett. You see the surname of the two authors is what it's named for, BB, and it's in the year 84. So this is the leading quantum cryptography protocol. But this is different than post-quantum cryptography. This is completely different. This is based on quantum key distribution. And quantum cryptography is still in the area of the physics. I wish I could make this work. This would be really fun thing to make it work. And one day we will have it, but today we're still the only operational algorithms that we have to protect against quantum cryptography. Quantum computers is not quantum cryptography, it's post-quantum cryptography. This is based on mathematics, this is based on physics. So let's see if there's something here that we need to cover, and I think this is probably a good time to end this section. Again, as you can see, it has taken, I don't know, I'm gonna have to watch the time of this video, but I need to cover all those things in the schedule. So I need to cover all those things in 15 minutes, and I have covered only the first one. Then I still have the second, the third, the fourth, and that's the difference between the preparation for delivering a lecture and the actual lecture. So in the actual lecture, you only choose the one or two most vivid examples, and you use those. You don't actually go through all the examples that I showed you here. Just there's not enough time, and people are busy. They cannot wait for you to explain this slowly. So if you want to subscribe to the YouTube channel, you're gonna get these videos as I'm recording them. But if you want to watch the final version, you can go to O'Reilly. If your organization or your university has a subscription, this is gonna be on the 2nd of September. So I hope to see you in the next video, and either on YouTube or with O'Reilly. See you in the next one.